let us, as I said in the morning class, if we want to solve a inhomogeneous equation, we have to first solve a homogeneous equation, ax equal to 0, and then write down all the solutions. And to find out all the solutions of ax equal to b, I will find out a particular solution. A particular solution can be found by giving the non-pivotal variables can be given value 0, yeah, and then find the values of pivotal variables. That will lead to a particular solution. Well, of course, we are under no condition to put the non-pivotal variables equal to 0. It just simplifies that. If we can assign arbitrary values to the non-pivotal variables and solve in terms of solve for the pivotal variables, and that will give me a particular solution of ax equal to b. Now, this is true if the matrix, when you write the matrix in row echelon form and they look at the bottom rows, they should be all 0 rows. And the bi's in front of 0 rows should be 0. If any bi in front of the 0 row is non-zero, then there is no solution to the system. Yeah. So we consider ax equal to b. This is the consistency condition that the first r rows of the coefficient matrix in the row echelon form are the non-zero rows. The remaining rows are 0 rows, and so br plus 1, br plus 2, bm must be 0. Yeah? Then only the system has a solution, if and only if. Yeah? So this is the consistency condition. So if my coefficient matrix of a system linear equation is in row echelon form, we can just look at this coefficient matrix, augmented matrix, and determine whether there is a solution or not. And this is the consistency condition, that the non-zero rows should have br plus 1, bm equal to 0. Yeah? Otherwise, there is no solution. So suppose the consistency condition is satisfied. The consistency condition is satisfied. Then we obtain a particular solution first of ax equal to b, simply by substituting the non-pivotal variables equal to 0. Yeah. So if the consistency condition is satisfied, there is at least one solution, and quite often there are infinitely many solutions. Okay. So to find a particular solution of ax equal to b, we can just set all the non-pivotal variables equal to 0. That is this condition that xk equal to 0 if k belongs to L1, L2, Ln minus r. Okay. Then we determine the pivotal variables. The pivotal variables are xk1, xk2, xkr, and by using back substitution, we can find out the pivotal variables. Okay. So we obtain these n minus r basic solutions of ax equal to 0 as follows. So we have found a particular solution, and now to find out all solutions, we have to look at a solution of the solutions of the homogeneous equation. Okay. So now we will look at first ax equal to 0, and we want to find out finitely many solutions of ax equal to 0, so that every solution of x equal to 0 is a linear combination of these finitely many solutions. These are called basic solutions. Okay. So we determine the pivotal variables by back substitution. So r variables are determined. The remaining n minus r are free variables. And we will see that there are n minus r basic solutions. These are called basic solutions. And every solution is a linear combination of basic solutions. Let us see how we do that. Okay. So the free variables are corresponding to the columns L1, L2, Ln minus r. So we take a free variable. Yeah. We look at the free variables. Suppose we have 3 free variables. Yeah. So we can find particular solutions by substituting any values of the free variable. So what we do is take these free variables, and one of the free variables we will set equal to 1. Say xk we set to 1, and other free variables we set to 0. Okay, and then we determine the other solutions corresponding to the pivotal variables. So the values of pivotal variables are determined in terms of the values of the non-pivotal variables. So among the non-pivotal variables, xl1, xl2, xl minus r, we give value 1 to one of the non-pivotal variables, and other variables are given value 0. Then we find these solutions called SL. So there are we find the solutions of homogeneous equation Ax equal to 0, and there are as many solutions in this manner as the number of free variables. Yeah. So corresponding to non-pivotal variables, we find these solutions SL. I am writing this SL. So SL is a particular solution of Ax equal to 0. How we determine SL? Well, put the non-pivotal, line up the non-pivotal variables, pick one of the non-pivotal variables and give value 1 to it, and the other non-pivotal variables we will give value 0. And this will lead to a solution of Ax equal to 0. Because earlier we said that if I have a consistent system Ax equal to b, then we can assign arbitrary value to the free variables to determine the values of the pivotal variables, and thereby we will find a particular solution. Now my system is Ax equal to 0. To find, I know that A is in row echelon form, and consistency condition is satisfied because x equal to 0 is always a solution. Okay? If I have a homogeneous equation, then consistency condition is satisfied. And so I start constructing particular solutions of Ax equal to 0. But this is the algorithm that I'm specifying to find particular solutions. We give value 1 to a free variable and value 0 to other free variables. The non-free variables, which are the corresponding to pivotal columns, are anyway going to be determined by the values of the free variables. So we can find out these n minus r solutions SL. Okay, and so this will lead to n minus r solutions, and these are called basic solutions of Ax equal to 0. Okay, these are called basic solutions, right? Yeah. Why are we obtaining exactly n minus r solutions of Ax equal to 0? Okay, so this will become clear by this proposition that all solutions of Ax equal to 0 are linear combination of the basic solutions that I just constructed, one for each non-pivotal variable. So there are these n minus r non-pivotal variables. They are the free variables, and corresponding to those free variables, I described a method to obtain particular solutions of Ax equal to 0. Then let me show that any solution of the homogeneous system can be obtained by taking linear combination of SL1, SL2, SLn minus. Okay, so let's prove that. So take S to be any solution. Okay, S is any solution of Ax equal to 0. Look at y equal to S minus, take real numbers RL1 multiply by SL1. SL1 is a vector. Yeah, SL1 is a solution, so it's a vector with n components. Take SL2, that's the second basic solution, and so on. And so I'm taking a linear combination of these n minus r solutions, and the coefficients are arbitrary real numbers. And S is any solution. Now you subtract from S this linear combination of the basic solutions. Okay, I want to show that y equal to 0. If I show that y equal to 0, then S will become a linear combination of these SL1, SL2, SLn minus r. Okay, so that will prove that all solutions of homogeneous system Ax equal to 0 are obtained as linear combinations of these basic solutions SL1, SL2, SL minus r. Yeah. So to show that y is a solution, you just operate y. Yeah, operate a on y. So ay is equal to as minus rl1, asl1, rl minus r, asl minus r equal to. Now this is 0 because as equal to 0. Because s is a solution of ax equal to 0. So as equal to 0. Now ASL1, ASL minus R, they are also equal to 0 because I determined SL1, SLn minus R to be solutions of AX equal to 0, right? So, and earlier we showed that if I take linear combination of a homogeneous system of equations, and then and if those are solutions, then any linear combination of solutions is also a solution. So AS equal to 0 and RL1, ASL1, RL minus R, ASLR, this is equal to 0. So AY equal to 0, right? So AY equal to 0. But if you just write down the structure of SL1, SL2, SLn minus R, yeah, just write the structure. The structure was that one non-pivotal variable was set to 1 and other non-pivotal variables were set to 0, and then the remaining variables which are corresponding to pivotal variables were determined from these particular values of non-pivotal variables. Yeah. So if you now this equation says that y is a solution. I want to show that y is equal to 0. Yeah, but you can just look at the kth entry of y, and it is actually 0 for every k in L1, L2, Ln minus R. Yeah, you can just check this equation. So y becomes 0 and ay is 0, and that shows that S is a linear combination of these. This will become clear if you write an example. There are just lots of notations here. Yeah, so S has become a linear combination of this basic solution, and so this is what this proposition says, that this gives an algorithm to find all solutions of AX equal to 0 by back substitution, provided A is in row echelon form. Okay. A is in row echelon form, then the homogeneous system AX equal to 0 has these solutions. These are linear combinations of basic solutions. Okay. So if the consistency condition is satisfied, then the general solution of AX equal to B, we determined a particular solution of AX equal to B. Yeah. So particular solution of AX equal to B was determined by setting all the non-pivotal variables equal to 0, and then pivotal variables were determined from there. That was one particular solution, and we proved earlier that to find all solutions of AX equal to B, it is enough to find one particular solution, and you add that particular solution to each and every solution of the corresponding homogeneous system of equations A equal to 0. Now we know all the solutions of AX equal to 0, they are linear combinations of these basic solutions, and we have determined one particular solution, and therefore we add this particular solution of x0 to a arbitrary solution of AX equal to 0. Arbitrary solution of AX equal to 0 is a linear combination of SL1, SL2, SLn minus R, and x0 is a particular solution. So every solution looks like x0 plus linear combination of these basic solutions, right? So let me show you an example. There were just lots of notations here. This will become clear. Suppose this is my row matrix in row echelon form. First you have to check that it is in row echelon form. And here there are 6 columns and four equations and 6 unknowns. 4 equations and 6 unknowns. And there are 3 pivots here. As you can see, the first row has pivot 2, the second row has pivot 3, third row has pivot 1, and the pivot 3 is to the right of pivot 2. It's not below it, it's not to the left of it, it is to the right. And the pivot 1 is to the right of pivot 3, and so on. So this, and the 0 rows are at the bottom of this matrix. So this matrix A is in row echelon form, and there are 4 equations, and the right hand side of those in 4 equations were B1, B2, B3, B4. They are stored in this column, B column. Okay. So this we now run the algorithm that I just described. Okay. So how do we? So there are several steps in finding all these solutions. We first find a particular solution. To find particular solution, as I said, all the non-pivotal variables are set to 0. And then you determine the pivotal variable. That will give me a particular solution. Yeah. So 2, 4, 5, they are the 2, 4, 5. They are the column numbers in which the pivots are sitting. So they are so K1 is 2 and K2 is 4 and K3 is 5. And the non-pivotal variable columns are first columns and the third column and the sixth column. So these are the non-pivotal columns, and therefore L1 is 1, L2 is 3, and L3 is 6, and R is 3. There are 3 non-zero rows in this matrix, and there are 3 pivots also. Okay. So we have classified the columns into two kinds, the non-pivotal columns and the pivotal columns. This is necessary to do to solve the system. Yeah. So here B4 is 0. You see the last row of A is the 0 row, and in front of that B4 entry is 0. Therefore, consistency condition is satisfied, and so this system has a solution. Yeah. So to find particular solution, you set 1, 3, 5, x1, x3, x5, x6 equal to 0 because they are corresponding to the non-pivotal columns. They are free variables. We can assign any values to them. So to find one particular solution, I can set all of them to be 0. Yeah. Now you look at the third equation. The third equation is x5 plus 2x6 equal to 2. The third equation has 1, 2, and 2. So it is x5 plus 2x6 equal to 2, and x6 is given value 0. So x5 is 2, and so 3x4 plus 5x5 plus 0x6 equal to 1. That is the second equation. In the second equation, I have put x6 equal to 0, right? X6 is 0, and x5 we already solved, and therefore x4 can be found. So x4 turns out to be minus 3 in this case. So therefore, we go to the first equation. In the first equation, there is no x1. It begins with 2. So 2x2 plus x3 plus 0x4 plus 2x5 plus 5x6 equal to 0, right? That is the first row correspond to the first equation, and this gives me the value of x2 is minus 2. Okay, so all the non-pivotal variables are set to 0, and the pivotal variables are determined from the non-pivotal variables, and we have consistency condition is satisfied, and therefore we have found a particular solution. So this is the particular solution: x0, 0, minus 2, 0, minus 3, 2, 0. So these are the values of x1, x2, x3, x4, x5, and x6. Okay. So is that clear? I have determined a particular solution of the homogeneous system of equations. Yeah. But my given system is inhomogeneous. It is Ax equal to B. The column B column is a non-zero vector. So we are solving a inhomogeneous system of equations. And to solve inhomogeneous system of equation, it is enough to find one particular solution of Ax equal to 0. That is a homogeneous equation. We have just done this. Now we go to the homogeneous system and find out all the solutions using the algorithm of writing down the basic solutions. Okay, so basic solutions, there will be as many basic solutions as the number of pivotal, the non-pivotal columns, right? So basic solutions of Ax equal to 0. So I described an algorithm to find SL1, SL2, SL3, etc. But L1, L2, L3 here are 1, 3, and 6. So S1, S3, S6, these are the basic solutions. To find S1, we give value 1 to x1, and other non-pivotal variables can be set to 0. Yeah? Non-pivotal variables can be given any values. But to find the basic solutions, I have to set one non-pivotal variable equal to 1 and other non-pivotal variables to 0. And this choice leads to a solution because the pivotal variables will be anyway determined by these values. So if I put x1 equal to 1, x3, x equal to 0, I get the first basic solution. To get the second basic solution, I put x3 equal to 1, and then x1 and x equal to 0 to get s3. And now the third basic solution is obtained by putting the last non-pivotal variable, which is x6 equal to 1, and other pivotal non-pivotal variables equal to 0, I get s6. Okay. So S1, S3, S6, they are the basic solutions. Each non-pivotal variable determines one basic solution. So there are three basic solutions of the homogeneous system, and I showed a general proof that every solution of Ax equal to 0 is a linear combination of the basic solutions. Yeah. So general solution is given by x equal to x0 plus alpha 1 s1, alpha 3 s3 plus alpha 6 x6. So you can write down. Yeah. So to get basic solution, we can assign any value. No. So to get basic solution, we have to assign the values in this manner, that x1 is 1 and the other two non-pivotal variables are 0. Yeah. So you will understand why this is being done. What we are doing is, you remember this term linearly independent. We are finding linearly independent. Now the S1, S3, S6, their linear combinations exhaust all the solutions. It is because of this particular assignment that we have done. So you have to be careful. You can't get basic solutions to give just randomly chosen values to variables. Yeah. So this method of giving value 1 to x1 and 0 to x3, x6, and then x3, the other non-pivotal variable equal to 1 and x1, x6 equal to 0. It will ensure that these three solutions, their linear combinations exhaust all the solutions of Ax equal to 0. Okay. So this I proved in the proposition earlier. We can get basic solutions in other means, but this will give us the basic solution so that all solutions of Ax equal to 0 are linear combination of these three basic solutions. Okay. Yeah. So x equal to x0 plus alpha 1 s1 plus alpha 3 s3 plus alpha 6 s6, and as you can see, alpha 1, alpha 3, alpha 6, they are the arbitrary real numbers. Okay, so there are these 3 degrees of freedom, and that corresponds to number of pivots. I mean, the non-pivots give rise to the basic solutions. And now equate the components on both the sides. Yeah. So x0, yeah, x0, if you remember, x0 had 0 as the first component. So x1 is simply alpha 1. And x2 we can determine by equating x2 on both the sides. x2 will be minus 2 minus alpha 3 plus alpha 6 over 2 and so on. Yeah. So we can write down each and every value of the variable and write down a general solution. Okay. So any question so far?
No, sir, you have answered all of them.
Yeah. Okay. All right. So let me summarize what is the conclusion of these observations. So this is the conclusion for system of linear equations. So suppose this discussion assumed that my matrix is in row echelon form. Yeah. So we have m by n matrix which is in row echelon form. First, look at the number of non-zero rows. Okay, in the row echelon form, if R is the number of non-zero rows and if B is the column vector on the right in the system of linear equations, then this linear system Ax equal to B has no solution if Br plus 1, Bm, if one of these is non-zero. So the 0 rows are at the bottom of a matrix in row echelon form, and the quantities Br plus 1, Br plus 2, Bm, all of them should be 0 if the system has a solution. If any one of them is non-zero, then I have an inconsistent linear equation. Yeah, 0 equal to a non-zero real number. So that is an inconsistent equation. So there is no solution if one of the Br plus 1, Bm is non-zero. Yeah. And so assume that they're all zero, consistency condition is satisfied. So if we will get a unique solution if the consistency condition is satisfied and the number of non-zero rows is exactly the number of all there's no non-zero row. If r equal to n, if there are n, if there are n pivots, okay, there are n pivots and n variables, then all the pivotal variables are automatically determined. So we will get a unique solution, right? We'll get a unique solution if the number of columns is number of pivotal variables, because pivotal variables are determined in terms of non-pivotal variables. So if there are no non-pivotal variables, then pivotal variables are uniquely determined. Yeah. So, and there are if the consistency condition is satisfied and number of non-pivotal variables is less than the number of columns, then there are going to be free variables. As soon as we have at least one variable is a free variable, non-pivotal variables, there will, and consistency condition is satisfied, there will be infinitely many solutions, because the free variables are n minus r and they can be assigned any value, and this assignment will lead to a solution of Ax equal to. Okay. So this is the proposition that take a matrix in row echelon form. There are r non-zero rows. Then a linear system Ax equal to 0 has only the zero solution if and only if r equal to n. Right? Ax equal to 0 has a solution because consistency condition is satisfied. All the bi's are 0. Okay. So Ax equal to 0 has a, but there could be non-zero solutions. So when will there be exactly one solution? If there are no free variables. Yeah, all variables are pivotal variables. In that case, we will get zero solution only. And if m is less than n, then Ax equal to 0 will always have a non-zero solution. That is, if number of equations is less than number of variables. Look at the situation. We have two equations and say 4 variables. Yeah. So if 2 equations are there, the number of rows is 2, and therefore the number of pivots cannot exceed 2. And therefore, if there are 4 equations, and then there will be at least 2 free variables. Yeah. And free variables will give rise to basic solutions. Basic solutions are non-zero solutions. Because to construct basic solutions, I said one of the non-pivotal variable equal to 0, and other non-pivotal variables, one of the non-pivotal variables equal to 1, and other non-pivotal variables equal to 0. So, and this will lead to the values of the pivotal variables, and therefore I will get a non-zero solution. So if number of equations is less than number of variables, then a homogeneous system Ax equal to 0 has a non-zero solution, namely those basic solutions. Yeah? There will be some basic solutions corresponding to non-pivotal variables, right? So if there are more variables and less number of equations in a homogeneous system of equations where A is in row echelon form, then there is a non-zero solution. Yeah. All right. So, this was the discussion for solving a system of linear equations when the coefficient matrix is in row echelon form. Okay, we determined the basic solutions, and we showed that every solution of the corresponding homogeneous equation is a linear combination of basic. That is the first observation. Then we can find a particular solution if consistency condition is satisfied. Then any assignment to the free variables will lead to values of non-free variables. Okay, so we can find a particular solution by this method, and then translate all the solutions of homogeneous equation by a particular solution, and that will give us all the solutions of Ax equal to 2. Okay, so if I am given an arbitrary system of linear equations, my aim would be to convert this into a simpler system of equation so that the coefficient matrix is in low echelon form. So once the coefficient matrix is in low echelon, we have an algorithm to write down all the solutions of Ax equal to b.